Hi! Strong mountain bike brakes have become something of a benchmark lately. More pistons, more power, and more prestige. With new models coming out left and right, I wanted to see what the excitement was all about. But instead of buying into this trend, I decided to build stronger brakes myself. These are the TRP Quadiems. If you hadn't heard of them, don't worry. Your wheels barely know them either. With these, braking power is more of a suggestion than a command. But we're going to fix that today. You remember the good old mechanical lever, like a brake lever. Push on the long end and you get a big force on the short end. The factor tying both sides together is torque. Since torque equals force times distance, we get this equation when solving for the output force. The ratio of lever lengths, effort arm over load arm, is what engineers call mechanical advantage. Hydraulic systems are basically levers, but with fluids instead of metal bars. Pushing a piston with a certain force creates pressure. And because hydraulic fluids are uncompressible, that pressure spreads evenly throughout the system, which means it is the same here, here, and here. And if we hook up a second chamber with a bigger piston, then the pressure acting on the big piston will also be the same. That means we get an amplification of the input force by this factor, the ratio of the caliper piston area and the main piston area, the so-called hydraulic advantage. Multiplying the mechanical by the hydraulic advantage gets you the total advantage. This is a way to quantify braking power. I've linked a website down in the comments where you can compare different braking systems side by side. This list doesn't include factors like power delivery or flex, but it still gives a pretty good idea of how powerful a brake actually is. As you can see, the DHR Evos sit somewhere in the middle of the pack, and the Quadiems rank right at the bottom. But with the mods I've planned for my Quadiems, they'd shoot right up to second place, only topped by the strongest brakes currently on the market, the Trickstuff Maxima. If you want more power from your brakes, sure, you could just squeeze harder on the lever blade. But if you'd rather keep your fingers intact, you'll need to either upsize the caliper pistons or downsize the master piston. But there is a catch to all that juicy power. With great power comes great lever throw. See, when you pull the lever a certain distance delta y, the piston moves delta x. The relation of motion between the two is called the motion ratio. And it just so happens that the motion ratio is inversely proportional to the total advantage. That means, for a greater force at the calipers, you inherently get a longer lever travel. That is the deal. And with mountain bike brakes becoming more and more powerful, the lever travel can become quite excessive. This is why some brands use a linkage or a cam. The idea? Low mechanical advantage at the start, when the pads are not in contact with the rotor, so you get more piston travel. Then, once the pads hit the rotor, the leverage ramps up for more power and better modulation. Sounds nice, but there is another trade-off. Mechanical advantage also helps to overcome the force of the return spring. So, when it's low at the start, you need to push harder with your finger compared to non-linkage brakes. This is the case for the SRAM Mavens, which have a reputation for their heavy lever feel, even though the return spring isn't overly stiff. So then why doesn't the Maxima with its distinct lack of linkage feel like you're just squeezing a sponge? Well, it would, were it not for a neat trick from Trickstuff. They set the gap between the rotor and the pads at only 0.15 millimeters, almost half of what you'll find on most brakes. Combine that with a stiff construction, and the bite point ends up feeling a lot closer to more conventional brakes. Alright, now that we understand how brakes should work, here's what I'm going to do. I'm going to swap the current 10mm piston for an 8mm one and increase the braking power by 56%. These are the three things we need to look at to get this mod to work. First, we need to make sure the lever can be pulled far enough without it hitting the handlebar. Second, we need to check that the piston has enough available travel inside the master cylinder body before bottoming out. And third, we need to examine if the seals on the piston can be positioned correctly. Looking inside the reservoir, you can see two holes. The upper hole, the fluid inlet port, connects the reservoir to the brake line, so that fluid can get into the caliper to compensate for pad wear, and air can get out to separate air bubbles from the braking system. As soon as the piston moves, the seal covers the inlet port and traps fluid in the brake line. The secondary seal on the piston needs to be placed far enough to the back so that it never gets past the bottom compensating port, even at full compression. Otherwise, the fluid from inside the reservoir could spill out, as would be the case in this animation. I made a graph of lever versus piston travel to see how far the lever needs to move with the smaller piston. Right now, my lever moves 32 mm at full pull, which pushes the piston by 5.9 mm. Since the 8 mm piston has to travel 56% farther to push the same volume of fluid, it now needs to travel 9.3 mm. That means the lever would have to be pulled 52 mm. Sounds bad, but yes, both the lever and the piston travel are in an acceptable range that will work with the mod. With all that in mind, I'm pretty confident to start building. For the material of the piston, I picked PEEK, a fancy plastic with PEEK mechanical properties. I know that at least one other brand has adopted it in their designs. To reduce the diameter of the main chamber, I'm going to make an insert out of a tube off of Amazon. Despite the listing clearly indicating 8 by 10 by 100 mm, these tubes actually turned out to be a
pack of 3 6063 aluminium round tube, 0.31 inch inner diameter aluminium tube, 0.39 inch outer diameter aluminium profile metal tube, 3.94 inch length aluminium tube for industrial construction craft.
Lucky me, the outside diameter is already 9.9 mm, which means these tubes will fit right into the original 10 mm bore. W Imperial system, I guess. Now, let's build this sucker. First, I assemble and calibrate my precision lathe. The methods I have tried so far are filing, sanding, sawing, cutting, and shaving the piston to shape. But there is one method which stood out as the most efficient of them all. This is the diameter I want for the piston. So I simply use my calipers and go to town on the plastic rod. This may not be the most elegant solution, but it gets you results. I also need a 3 mm wide groove for the primary hydraulic seal, and the thickness of these calipers happens to be just that. This really is the perfect tool for the job. Since the reservoir is separated from the pressurized brake line, the secondary seal can just be a basic O-ring. Now I just have to create a pocket for the round end of the piston rod and finish the job with polishing. To make the insert, I lightly polish the outside of the tube, stick it inside the lever body and drill 2 holes for the ports. 1.5 mm for the compensating port and a tiny 0.5 mm hole for the inlet port. A bigger hole would lead to more backflow, which can change the fluid volume inside the brake lines. The Shimano brakes sport not 1 but 3 unusually large ports, which is pretty much why their bite point keeps wandering more than the mind of a sex offender in a yoga class. Next, I cut the tube to length and polish the inside. To bond the insert in place, I'm going to use Loctite 638. The issue with this type of adhesive is to get it to remain between the bonding surfaces when the insert is pressed in. Therefore, I'll create some nice cushy channels where the Loctite can sit in and stay where it needs to be. Loctite cures in the absence of oxygen, so you've got plenty of time to clean up the mess before it turns into green concrete. I chose the more expensive PU seals over typical NBR because of their long life expectancy. However, these little bastards turned out to be stiffer than YouTube's guidelines on dick jokes, and getting these on the piston has proven to be quite a challenge. Great success! I also decided to use the softer Shimano spring for less finger fatigue. Time to bleed. Bubbles coming up from the inlet port is a great sign because it means I didn't cock up the positioning of the main seal. Now it's time to do it properly and see how the brake feels. Also, here's the obligatory warning. Modifying your brakes is dangerous. Don't try this unless you know what you're doing. I already converted my rear brake, tested it thoroughly and triple checked for leaks. I have done the necessary calculations, but if you're an inexperienced scrap engineer, brakes are probably not the best place to start. Well, the lever throw is definitely longer, and it turns out to be almost exactly as long as we predicted in our calculations. Yay! Now to test it on the trails.
Alright, I'm going to test these out on a pretty fun trail. It's steep and has a lot of switchbacks, so it should be perfect to see how these brakes work. Anyway, see you at the top. Well, that was easy. I actually forgot to bed in the brakes, so it might be a little squeaky for a while. Okay. So far so good. Oh boy, friend or foe? So was Dankeschön.
Der pfeift so. Hier, sorry, was hörst du das pfeifen?
Okay, so the pads are definitely bedded in right now. And you can feel the increase in braking power, that's for sure. But it's still freezing out here, and my fingers are starting to get numb. Whew. Man, what an awesome trail. Oh. Okay. Smooth. Oh, not so smooth. Oh boy. Ah, damn it. Okay. Okie dokie. So, what's the verdict? Well, to no one's surprise, these brakes actually feel a lot closer to the DHR Evos than the Quadiems. They actually feel like the Evos but with more braking power, which in my opinion is the perfect combination. The Quadiems used to have a really defined bite point and these are quite the opposite. You just basically pull the lever and then all of a sudden you get all the braking power. But I think I'll get along with these brakes just fine.
Personally, I don't mind the long lever throw because I brake with my middle phalanx and pretty much always have the levers pulled anyway. But in order to really make this brake work, I would need a contact adjuster to reduce the distance between the pads and the rotor. Cascade Components' fancy brake adjuster might be useful on that front, or I could just build something on my own. Maybe I could even get a hold of those fancy trick stuff caliper piston seals to move the pistons further out. I don't know.
Let me know if you'd like to see me do that. But for now, ciao.
Und warum ist die verkehrt so? Beim Arsenal war 100